Welcome to Lesson 16, Unit 2, Solving Systems by Elimination, Part 3. Today's learning goal, let's find out how multiplying equations by a factor can help us solve systems of linear equations. We have our warm-up. They give us an equation, x plus 5 equals 11. What is the solution to this equation? So, if we're trying to solve this equation, we would subtract 5 from both sides, and that would give us x equals 6. So this would be considered the solution to this equation. If we multiply both sides of the equation by a factor, say 4, what equation would we have? So now if we think about x plus 5 times 4, let me change how I wrote that. We'll say 4 times x plus 5 equals 4 times 11. If we use distribution, 4 times x becomes 4x. 4 times 5 becomes 20. And 4 times 11 becomes 44. So this would be our new equation. Now they want to know what is the solution to this equation. So we would take 4x plus 20 equals 44. We would get rid of the 20 by subtracting it from both sides. That would give us 4x equals 24. We would divide both sides by 4, and we would end up with x equals 6. So we can see that we still have the same solution, even if we multiply everything through by 4. Then they ask, what if we multiply both sides by 100? So if we multiply everything by 100, x times 100 would be 100x. 5 times 100 would be 500. And 11 times 100 would be 1,100. We would subtract the 500 from both sides, and we would have 100x equals 600. We would divide both sides by 100, and again, we would end up with x equals 6. So we did the same thing to both sides of the equation. We created an equivalent equation, and we got the same answer in both instances. And one last thing they want us to try is multiplying both sides by 0.5. So x times 0.5 would be 0.5x. 0.5 times 5 would be 2.5. And 11 times 0.5 would be 5.5. We would subtract 2.5 from both sides. We would get 0.5x equals 3. We would divide both sides by 0.5, and we would end up with x equals 6. So you can see that in every single instance, multiplying both sides of the equation by the same factor results in an equivalent equation that gives us the same solution every time. Is the solution to each of these equations still x equals 6? Yes, it is, and we just showed that. What if we multiply both sides of a two-variable equation by the same factor? Would the resulting equation have the same solutions as the original equation? As long as we are doing the same thing to both sides, we are still creating an equivalent equation. So now it says consider two equations in a system. We have equation A and equation B. Use graphing technology to graph the equations, then identify the coordinates of the solution. To do this, we can use Desmos calculator. We have an equation 4x plus y equals 1. So that would be this red line here. Then we also have x plus 2y equals 9. That would be this blue line here. Then identify the coordinates of the solution. Well, that would be this point here where they intersect. And we see that our coordinate would be -1, 5. So we can go ahead and write that up here. -1, 5. Write a few equations that are equivalent to equation A by multiplying both sides of it by the same number. For example, 2, -5, or 1/2. So, if I multiply the first one by 2, 4x times 2 is 8x. Y times 2 is 2y. And 1 times 2 is 2. If we multiply by -5, -5 times 4x is -20x. Y times -5 is -5y. And 1 times -5 is -5. And finally, we're going to multiply everything by 1/2. 4x times 1/2 is 2x. Y times 1/2 is 1/2 y. And 1 times 1/2 is 1/2. Now they want us to graph these equations that we generated. So 8x plus 2y equals 2. Notice it lays right on top of the red line. That is because they are still the same line. They are still equivalent to each other. Next one is -20x minus 5y equals -5. So minus 20x minus 5y equals -5. Notice the purple line got drawn right on top of both the red and green line. So we still have the exact same line, we just have a multiple of it. And finally, 2x plus 1/2 y equals 1/2. And notice the black line gets drawn exactly on top of all three of the previous lines. This is because multiplying an equation by the same factor just creates a multiple of that line. So when you graph them, you are still graphing the exact same line. How can we explain the identical graphs? We explain them because every part was multiplied by the same factor. So the very first thing you would end up doing is dividing them all by that factor to get back to the original equation. So we graph the exact same line and they would have the exact same solutions. What move was made to generate A1, A2, and A3? We multiplied the original equation A by the same factor on every part of the original equation A. Why did it create equations that are equivalent to A? Because all we did was multiply every part by a factor. When we would go to solve this, we would end up dividing by that same factor to get x by itself. Therefore, we would end up just recreating the exact same line. If we created a table with x, y values for each equation, how would the values compare? They would all be exactly the same. Every x value would be paired with the same y value. How can you use what you've learned about isolating a variable to show that the equations are equivalent? You can substitute any value in for x and then solve it for y and show that you would get the same answer. Here is a system you solved by graphing earlier. So this is that equation A and equation B again. To start solving the system, Elena wrote 4x plus y equals 1 and 4x plus 8y equals 36. Then she wrote 4x plus y equals 1 and 4x plus 8y equals 36. And she subtracted the bottom equation from the top equation to get negative 7y equals negative 35. So what were Elena's first two moves? Well, the first thing she did was multiply equation B by 4. Then she subtracted equation B from equation A. Okay. Now it says complete the solving process algebraically. Show that the solution is indeed x equals negative 1 and y equals 5. So once we have negative 7y equals negative 35, we're going to divide both sides by negative 7. This gives us y equals 5. Now I take y equals 5 and I plug it back into either one of these top equations. So we could say 4x plus 5 equals 1. We would subtract 5 from both sides, and we would get x equals -4. Now we would divide both sides by 4, and we would get x equals -1. Therefore, our solution is the point -1, 5. So we've again proven this is true. So now they want to know, what do you notice about the graph of the equations? On the left, we have the original equations, and on the right, we have Elena's equations. So, if you notice, the blue line, the black line, and the yellow line all intersect at -1, 5. And this is because we have our first line, we graph our second line, our second line is then multiplied by 4, so the bottom equation on the originals and the top equation on Elena's are the exact same line. Then we have it where we eliminated one of the equations and we were able to get the yellow line. But every single one of them actually intersects at -1, 5, which is what we said the answer was. So here are the two equations in the original system. In solving the system, what do we assume about the x and y values in the equations? We didn't use the original two equations to solve. Instead, we multiplied each side of equation B by 4 to get equation B1. How do we know that the same x-y pair is also a solution to equation B1? This is because we created an equivalent equation by multiplying every part of the equation by the same factor. We couldn't yet solve the system with equations A and B1, so we subtracted B1 from A and got equation C. How do we know that the same xy pair from earlier is also a solution to equation C? Because if we say that everything on the left side equals everything on the right side, then when we subtract the left side of the bottom equation from the top equation, and we subtract something that we said was equal to it on the right side, we're actually subtracting equal amounts from the left and the right. Therefore, we're going to have an equivalent equation that still has the same answers. Solving equation C gives us y equals 5. How do we find the x value? We substitute 5 into the original equation for y, and we solve for x. If we substitute this pair of values for x and y in equations A, B, B1, and C, and evaluate the expressions, can we expect to find true statements? Yes, this is why we can see on the graph that these lines intersect at -1, 5, because they all are made true by that point pair. Equivalent systems are systems with the exact same solution set. Suppose we want to solve the system by first eliminating the y variable. What factor should we choose? Which equation should we apply to it? Could we multiply equation A by 6 and multiply equation B by -3 as a way to eliminate the y variable? So in this next exercise, we're going to do a card sort. I will give you some slips of paper with systems of equations written on them. Each system represents a step in solving this system. Arrange the slips in the order that would lead to a solution. Be prepared to describe what move takes one system to the next system. Explain why each system is equivalent to the one before it. So, the cards that I gave you would go in this order. Now we can look and see what happened in each one that led to the next step. So I can see that we went from 4/5 x to 4x. That means we multiplied everything in this top equation by 5 to get to the next one. Now I see that we went from negative x to negative 4x, so we multiplied everything in the bottom equation by 4, and we got the new equation. Now we can see that our negative 4x has gone away. So what we did was we we added the bottom and the top, and we got the new equation on the bottom here. Now to go from this bottom equation to this bottom equation, we divided both sides by 102. Now we have a value for y. So what we did was we took that value of y, we substituted it into the top equation for y, and we got 35. Now we can see that we subtract 35 from both sides to end up with 4x equals 40. And finally, we can see that we divided both sides by 4 to get x equals 10. So on our last card, we actually have our answers: x equals 10, y equals 7/6. So now they say, here is a system of equations. To solve this system, Diego wrote these equivalent systems for his first two steps. So we have step 1. We can see that 8a is now negative 40a. We can see that b is now negative 5b, and we can see that 11 is now negative 55. So it looks like they multiplied the bottom by negative 5. Now we see that if we add these together, our b term disappears. 12a minus 40a got us negative 28a, and negative 15 minus 55 got us negative 70. So it looks like they added together. Write another set of equivalent systems different than Diego's first two steps that will allow one variable to be eliminated and enable you to solve the original system. Be prepared to describe the moves you make to create each new system and to explain why each one has the same solution as the original system. So, if we have our original equations here, instead of multiplying by negative 5, we could have multiplied by positive 5 and subtracted. Or, if we're trying to get rid of a, I could multiply everything on the bottom by -1.5. If I do that, then I have 12a plus 5b equals -15. 8a times -1.5 is -12a. B times -1.5 is -1.5b. And 11 times -1.5 would be -16.5. Now if I add these together, 12a minus 12a is 0. 5b minus 1.5b gives me 3.5b. -15 minus 16.5 would give me -31.5. Now I would divide both sides by 3.5. And we would find out -31.5 divided by 3.5 equals -9. Now if b is -9, then I could say 8a minus 9 equals 11. Add the 9 to both sides. 8a equals 20. Divide both sides by 8. And a equals 2.5. So our answer would be 2.5 -9. Use your equivalent systems to solve the original system, then check your solutions by substituting the pair of values into the original system. So my original one was 12a plus 5b equals -15. So 12a plus 5b equals -15. We said a equals 2.5 and b equals -9. Twelve times 2.5 would equal 30. 5 times -9 would be -45. And 30 minus 45 would be -15. That does work for the top equation. The bottom equation was 8a plus b equals 11. So that would be 8 times 2.5 plus -9 equals 11. 8 times 2.5 is 20. 20 minus 9 equals 11. So it does solve our system of equations. So now they want us to explain what move takes one system to the next. How do you know the new system is equivalent to the one before? And they give us this table to fill out. So the first step is the original. Nothing has changed. We just wrote them down. So this is both. Nothing was done yet. And this does not apply. There are no previous ones. In step 1, we see that the top equation has been multiplied by 5. So 4/5 x plus 6y equals 15. This was multiplied by 4, and it's equivalent because the same thing was done to both sides. Next, to go from step 1 to step 2, we multiplied the bottom by 4. Oh, and I messed up here. In this one, we multiplied by 5. So now we had the bottom multiplied by 4. And again, we did the same to both sides. Next, to go from step 2 to step 3, we added the top and bottom. So this is both. We added them. So we added equal left and right. Next, to go from 3 to 4, we can see that we divided the bottom by 102 on both sides. So this is the bottom divided by 102, and the same was done to both sides. To go from 4 to 5, we substituted 7/6 into the top for y. So these are the same because we're substituting an equal amount in for y. To go from 5 to 6, we can see that we subtract 35 from both sides. And again, they're equal because same thing, both sides. And finally, to go from 6 to 7, we divided both sides of the top by 4 so we could solve for x. And again, they are equivalent because we did the same thing to both sides. So, the learning targets in this lesson, number 1, I can solve systems of equations by multiplying each side of one or both equations by a factor, then adding or subtracting the equations to eliminate a variable. And learning target number 2, I understand that multiplying each side of an equation by a factor creates an equivalent equation whose graph and solutions are the same as that of the original equation. If you feel comfortable with both of these learning targets, then you are on track for our test on the 3rd. If you still have questions, please ask those during class so I can clarify them for you before your test. So we have our cool down. It says Lynn and Priya were working on solving this system of equations. Lynn's first move is to multiply the first equation by 3. Priya's first move is to multiply the second equation by 2. Explain why either move creates a new equation with the same solutions as the original equation. It doesn't matter what you multiply by, as long as you multiply every part of the equation by the same number. This just gives you a multiple of the original equation, and you will still have the same exact solutions. It is still the exact same line. Whose first move would you choose to do to solve the system? Explain your reasoning. So either one of these would work. If I use Lynn and multiply the first equation by 3, I get rid of that fraction, and then I could subtract the bottom from the top. If I used Priya's, then I would turn y into 2y, and I could subtract the bottom from the top. Either way is correct, but I would personally use Lynn so that I could get rid of the fraction because I want to get rid of them as early as possible. Our glossary terms for this lesson: elimination, a method of solving a system of 2 equations in 2 variables where you add or subtract a multiple of one equation to another in order to get an equation with only one of the variables, thus eliminating the other variable. Equivalent systems. 2 systems are equivalent if they share the exact same solution set. Solution to a system of equations. A coordinate pair that makes both equations in the system true. On the graph shown of the equations in a system, the solution is the point where the graphs intersect. Substitution. Substitution is replacing a variable with an expression it is equal to. System of equations. Two or more equations that represent the constraints in the same situation form a system of equations. So if you have any questions, please make sure you ask those during class so that you will have everything you need for the test on the 3rd.